All right, people, so we are back and we are talking about making equilateral triangles or other equilateral shapes where all sides are the same. So I've highlighted the words that I think that you guys are going to struggle with a little bit to make it a little easier as we're going through and talk about each of those words as we go through. But today's lesson is pretty straightforward. We're talking about shapes fitting inside of circles. So we're talking about eventually we're going to get to where we make a circle and then we're going to put a shape inside that circle and then talk about their sides, okay? And then talk about how those circles and shapes relate. So that's really kind of our goal, and then understanding, getting a deeper understanding of what that means, okay? So like a rhombus, so a rhombus has four sides. An equilateral triangle has three congruent sides. Okay, so an equilateral triangle has three congruent sides. So congruent we can kind of look like as equal. It's not exactly equal, but it's really close to equal. So we can reread this as an equilateral triangle has three equal sides. Okay, show and describe how you might locate the third vertex. Okay, so vertex is a point on an equilateral triangle. Okay, so equilateral, so all sides being the same, given that ST below as one of the sides is the equilateral triangle. So we have our ST down here. So if we know that our equilateral triangle has all equal sides, and we're looking for a third point, we know that the other 2 points, sorry, you guys aren't even seeing the ST yet. So we know, here's ST. So we know that this length has to be the same length as the other side. So our equilateral triangle has to be somewhere right up here, right? And we can kind of double check that by taking a piece of paper and just putting a dot there to get our distance and see how close we got, right? So maybe we're not as close as I thought. The other thing, if we know it's the same distance, we know it's got to be right in the middle. So let's make a third dot right here. And we can make our line going straight up and down. Okay, so we know it's perpendicular, so it's going to end up in the middle. And we have our 2 dots here, and we're going to, oh, there it is. So we're going to connect it right there. Okay, so there's one side, and there's the other. Okay, so we have an equilateral triangle. All sides are congruent to each other. Okay, so I would describe that as we found the distance, found the length, length of ST, and use that for the other 2 sides. For the other sides. Okay, so we used it for the other sides. All right, so we first found ST and then we used that to figure out the other 2 sides. Okay, all right, so moving on here down to the next one. It says, to construct a parallelogram, so construct meaning build, right? To construct a parallelogram, we need to be able to construct a line parallel to a given line through a given point. For example, suppose we want to construct a line parallel to a segment AB. So segment AB, right? So it's parallel to AB, okay? Through point C in the diagram below. Since we have observed that the parallel lines have the same slope, the line through point C, which will be parallel to AB, only if the angle formed by AB is congruent to ABC. Okay, so they're saying if our angle ABC, they're talking about this angle, has to be congruent to whatever this angle is going to be to get our line coming up this way. So if we're making a parallelogram looks like this, right? It's got 2 parallel sides. This is parallel to this. This is parallel to this. They're saying that this angle has to be congruent to whatever this angle is, right? So we can match that angle up, and that'll tell us our line that is it's going to get created later on. Okay, so can you describe and illustrate a strategy that will construct an angle with the vertex point C? So I would say start off with this guy, and we're going to get our length here. So we know that point B is right there, right? Boom. And we can connect, get our angle in there. So I'm kind of just copying our angle, right? And I'm going to move this over to point C. So I'm going to just try to match that up as best as I can. And then that actually makes sure that we have the same angle, and I can copy this line coming up here. Okay? And then I just fill in the blank right there. All right, and then we can take our angle again, and we can draw it out of there. Okay, and then we have our parallelogram. Okay, so what did we do? We copied our angle, right? So copied angle, and we used that angle to draw a new line. Okay, so we copied the angle, we used that angle to draw that new line, all right? So when you get a parallelogram, you notice that this angle is congruent to this angle, and it's also going to be congruent to the angle across from it. We did talk about that the other day when we were going deep into shapes. And so we know that this angle is congruent to this angle, which is congruent to this angle. And we also know that these two angles, this angle and this angle, are going to be congruent as well for a parallelogram. So parallelograms have a lot of congruent angles in there that you can use to make sure that you end up drawing the right parallelogram. Okay, let's turn it over. All right, so now we're going to construct some more shapes. Okay, so it says, because regular polygons, so regular, when we see the word regular polygon, we're talking about all equal sides, okay? Okay, so because regular polygons have a rotational symmetry, so rotation meaning spinning, right? We're spinning, rotational symmetry. They can be inscribed in a circle. So inscribed just means fit inside. So fit inside a circle or inscribed in a circle. Excuse me. The circumscribed circle, so, excuse me. The circumscribed circle, so this circumscribed just means on the outside, okay? So the circle is on the outside. So if we had a circle, so everybody draw a circle on their page right up here, and we're gonna inscribe a triangle in there, okay? So if we inscribe, so this triangle is inscribed. Okay, and the circle is what we call circumscribed. Okay, so it's on the outside. Okay, so the circumscribed circle has a center at the center of rotation and passes through all the vertices. So vertices, so we're talking about these points, vertices are these guys. Okay, so it's passing through all the vertices of the regular polygon. So regular meaning equal sides, right? Regular equal sides. So we're saying that the center of this circle, okay, if the center of the circle matches up with the center of the triangle, then all of the points of the regular triangle or the equilateral triangle, all the vertices of that triangle go through and match up with that circle, okay? So that's what we're talking about with rotational symmetry, okay? So we're going to come down here and we're going to start with a hexagon, and it says, we might begin constructing a hexagon by noticing that a hexagon can be decomposed into 6 congruent equilateral triangles formed by 3 of its lines of symmetry. Okay, so if we're going to make an equilateral triangle, we might actually be able to do that by first making a circle, okay? So I'm going to give you guys some tools to make perfect circles, but the circle I have my circle is good enough for right now, but you guys can use, you guys will have tools to do that in class. So we're going to make a circle, and we're going to make 6 even lines going across our circle, okay? So we're going to have, there we go, and then, or 6 equal lines. So we have six parts to our circle. So we've seen this in, we saw this in the last chapter when we were saying, hey, what's the angle of rotation of this? And we took this, and since there were 6 pieces, we divided 360 by 6. Well, we started kind of hinting at where we're going for this and creating our parts and creating shapes by starting to connect each of these points, okay? So just be very careful as you're doing this so that when you look back from your homework, you actually have a good example. So we've got our, it's not perfect because I'm not perfect. We might begin by constructing, we have our hexagon, and we can decompose it into 6 congruent equilateral triangles. So you'll notice that these triangles have all the same sides, right? So we've sketched a diagram of our decomposition. So we have our 6 triangles in there, and you can do this with any equilateral or regular polygon. If it's in a regular octagon, it's going to have 8 equilateral triangles. And if you can start seeing the world in triangles, man, your world's going to get a little easier for math. Okay, based on your sketch, where is the center of the circle that would circumscribe the hexagon? Well, if you take a look at the center of the circle and the center of the hexagon, they're the same. So we can say that the center for both shapes is the same. Okay, so, and then it says the 6 vertices of the hexagon lie on the circle. So the 6 vertices, so we're talking 1, 2, 3, 4, 5, 6. So the 6 vertices, the 6 vertices lie on the circle in which the regular hexagon is inscribed. The 6 sides of the hexagon are the chords of the circle, okay? How are the lengths of these chords related to the lengths of the radii? Okay, so a radii is half the distance across the circle. So each of these, this is a radius. And a radii is just many radiuses, more than one radius, right? Okay, so the radii from the center of the circle to the vertices of the hexagon. Okay, so what do you, let's answer that question real quick. Okay, so how are they related? How is this radius related to this side? Well, they're the same. So question number 1, they are the same. The radii and the chords, okay, so our chords, so these are our chords. The radii and the chords are the same. Okay, so the radii and the chords are the same. That is, how do you know that the 6 triangles formed by drawing 3 lines of symmetry are equilateral triangles? Okay, so how do we know that though? So question number 2 is, how do we know that? So here's our hint. Consider the angles of rotation. Can you convince yourself that these 6 triangles are equilateral and therefore, or equal angular and therefore equilateral? Okay, so equal angular. So they're saying, do we know what the angles are? Do we know what the angle of rotation is here? Okay, so the angle of rotation is, well, we have 360, right? And we're going to divide that by 6 sides, okay? And we get 60 degrees. Okay, so if we know that it's 60 degrees for each angle of rotation, then what we know about our triangles are that we have what we know about our triangle is that a triangle has 180 degrees. Okay, so a triangle has 180 degrees in a triangle. And three angles in a triangle. There's three angles in a triangle. That's pretty straightforward. Okay, three angles times 60 degrees equals 180 degrees. That means all the angles are the same. So if all the angles are the same, then guess what? All the sides are the same. So that answers our question there. 180 degrees in a triangle. There are three angles that are 60 degrees. We know each of these angles is 60 degrees. And so if this is 60 degrees and these are all the same sides here, well then this has to be 60 degrees and this has to be 60 degrees. And so they're all the same. If they have all angles that are the same, then our triangle is an equilateral triangle. All right. I can answer more questions on that in class if we need to. All right. So now we're getting into the part where you're going to have to start doing some work, and it's not just going to be me telling you what to do. Okay, so based on the analysis of the regular hexagon and its circumscribed circle, illustrate and describe a process for constructing a hexagon inscribed in the circle given below. So I would say number one, draw diameters. Okay. Number two, make chords. Okay, so draw the diameters and then make the chords, and then you're going to have your circumscribed hexagon. Okay, so then you're going to come down here and you're going to modify your work with the hexagon to construct an equilateral triangle inscribed in the circle. So now you're going to make a triangle in the circle. Okay, so a triangle has three sides. So you're going to be talking about three vertices and three angles. Okay, so describe how you might construct a square inside a circle. So now is your job, right? I've shown you how to make a circle. You're going to draw the diameter. So here's the diameter. I'll draw one to get you started. Okay, so you're going to have to draw the others now and make the chords. And then down here, you're only going to be drawing three of them, and you should have them touching the points, right? I've drawn this triangle a couple of times. So this triangle is right up here. This triangle is right up here, right? So that's your job to get through this one. And then you're going to talk about how you would draw a square in a circle. So you're talking about making a circle, right? And then I want to know how you're going to make that square, okay? So this one is pretty straightforward. You've done this before. We've talked about image and we've talked about pre-image. So your job is to find which one of these lines is the image and pre-image, and that's pretty straightforward because you've got your primes there, right? I'm looking for the primes. And then you're gonna have to describe what is the line, right? Describe the transformation and then the equation of the pre-image and the equation for the image. So this is the y equals, and then you're gonna find your slope, mx, plus, and then you're gonna find b, right? And then you're gonna do the same thing for the next one, okay? Okay, so that's this page, this whole page. And then the next one, so now we're getting into the set. So this is what you're gonna be doing more on your own. And it says construct a parallelogram given by xy, so parallelogram. This is the very first one that we did in our lesson, so page 7, look back at page 7. And then it says construct a parallel line Q to QT, so parallel line to QT through point R, so your line's gonna look something like this. Number 7, I want you to look up what an isosceles triangle is if you don't, okay? So look it up in Google. And then the other two you should be able to create, read. In the Go section, I'm gonna give you a little instruction on number 9 in class, and then it's your job to go through here. So we're talking about the explicit functions for this one, so we're gonna go way back on this one. So I'm gonna give you a little instruction in class. So you guys can do it, I believe in you.